I can't make this bigger, but that's okay. That'll have to be okay. All right, you guys. So this is the same definition of a polynomial function that we looked at the other day. Okay, so just a reminder, n would be the degree of the polynomial. All polynomials can be written in this form. A sub n represents the leading coefficient. And then a sub 0 is the constant that would correspond to the y-intercept. Right, so the y-intercept would be 0, comma a sub 0. The graphs of polynomial functions are all continuous and smooth. And we've talked about continuity. So continuous meaning over their implicit domain of all real numbers, polynomials, their graphs, you could trace from negative infinity to positive infinity without ever having to lift up your pencil. There are no discontinuities in a polynomial function, right, Sid?
Yes.
You have the notes open right now. Join me. Smooth, meaning there's no sharp corners. An example of a sharp corner, a function that has a sharp corner, is like absolute value of x at x equals to 0. This doesn't seem important to us right now, but next year it will be important where the function is continuous, if there's any discontinuities, but also if there's any sort of like sharp corners or turns on the graph or cusps. But for now, smooth continuous graphs. A line, we got into this argument in my my calculus class the other day. You guys, a line is a curve. It's a curve. Graphs are curves. Okay. There are some that are curvier than others, but it's a curve. So just an example of like a polynomial function, smooth continuous curve where you'd never have to lift up your pencil. So if f of x is a polynomial function and a is a real number, then the following statements are true. And I know it's come up this year in discussion of using certain vocabulary incorrectly. So I want to try and correct that now. Anytime you are solving for an unknown is when you are solving something. You are solving an equation. You're solving for an unknown. So whenever you set your polynomial function, you set f of x, or you set the y equal to 0, and then you solve for the values of x that would make that a true statement, that's when you are finding the solutions to the equation, or the roots. So solution and root mean the same thing. That's coming from the equation where f of x has been set equal to 0 and you're solving for the values of x. Now, those solutions, and there can be more than one, there might be none, but there could be more than one, correspond to the x-intercepts on the graphs, which are points, right? A comma 0 represents the ordered pair, represents a point. X equal to A, which was also a solution to the equation 0 equals to whatever the polynomial rule is also what we call the 0 of a function, because if you evaluate your function at whatever A is, it would make the function value 0. So we call it a 0. And then if x equals to A is a 0, that means that x minus A would need to be a factor of the polynomial. Are we okay with that so far? When the value of a continuous function transitions from negative to positive and vice versa, it must pass through 0, meaning it must pass through the x-axis. So if the function is changing from positive to negative or negative to positive, it would have to pass through the x-axis. It's important to remember that the existence of a 0 does not imply the function will change signs. That's a typo. That should say will change signs. But if it's going to change signs, it's going to happen at the x-axis. This leads us into the intermediate value theorem. This theorem is one of those theorems that's kind of like, well, duh. Yeah, that makes sense. Like, it doesn't seem that profound, but it's an important theorem. We're not going to so much use intermediate value theorem in this class as much as like I'm planting the seed here. It's going to come up often next year. So if f is continuous on a closed interval. Now, for intermediate value theorem to apply, we have like these preconditions that have to be checked off for it to apply. The first of those preconditions is the fact that f has to be continuous. And it has to be continuous specifically on the closed interval from A to B. If it's an open interval, intermediate value theorem does not apply. Its implications might still happen, but it's not a given. And the function value at the endpoints of the closed interval can't be equal to each other. So I'm going to draw a picture to kind of demonstrate how intermediate value theorem or to make sense of intermediate value theorem, I should say. So let's say we have a curve. Draw something really basic. Let's say that this is f. And our closed interval will be from A to B. Okay, this point would be A comma f of A. This point would be B comma f of B. So on the closed interval from A to B, f is continuous. And the function values at the endpoints are different. So the intermediate value theorem here would apply. And what intermediate value theorem says is that k is a value between f of A and f of B. So k can be greater than f of A and less than f of B, but k could also just be greater than f of B and less than f of A. It's just a value that's between f of A and f of B. And when these three conditions, so f is continuous on the closed interval, the endpoints, the function value at the endpoints are not equal to each other. If k is between f of A and f of B, then it will be a function value on the interval from A to B. There will be a value C, at least one value, C, such that f of C would be equal to whatever k is. So that point would be C comma f of C, which is C comma k. And there could be multiple x values that have a y value of k. It's just you're guaranteed at least one point where the function value, the y value would be k. Annabelle.
This is kind of a dumb section, but for the other thing over there, how could it be like, how could k be?
K just needs to be between the endpoint. So f of A could be smaller than f of B, or f of B could be smaller than f of A.
Wait,
So if the function were decreasing,
oh, that's not where the F doesn't.
not this specific graph,
Oh,
I'm just saying in general,
okay.
one of these two statements would be true. So in other words, the intermediate value theorem states that for a continuous function f, if x takes on all values between a and b, then f of x must take on all values between f of a and f of b, or f of b and f of a. This is an existence theorem because it tells us that at least one number c exists, but it does not provide us with the method of finding c. Now, if a to b is continuous, you could think about using smaller and smaller closed intervals to kind of narrow down what c would be, like what the x value would be that would give you the function value. There's no like exact way of determining it. It's more like it proves the existence. When these conditions hold, it proves the existence of a function value. And intermediate value theorem questions come up often on the AP exam. So I'm planting the seed now. I'm going to show you where we could think about using it. We're not really going to do intermediate value theorem problems. Are we all tired? It's like, do we like a stretch break real fast or something? Or water? Can I go get water? Go get water real fast if you need to. We're not taking a big break, but go do that if you need to.
I also go get water.
Run quickly, and then I'm going to continue on. We're videoing. You were able to get boba? You between your appointment and here?
On the way.
Didn't take any extra time?
No. I didn't eat. I also got lunch and ate in the car.
What is boba? Is it tapioca?
Like, I ate chocolate.
Is that your lunch?
I had that in the car.
So enough to have a rule that if you get boba, then you get him some boba as well.
I remember that. Mr. Arnold. Am I able to pause the video? I can pause. Let's resume recording. That was our little break. So note, you guys, a function that is not continuous does not necessarily exhibit intermediate value theorem property. Now, all the function values between, like if you have an interval, like all the function values could still exist, but if it's not defined on a closed interval, if it's not continuous, intermediate value theorem would not technically apply. So what can we use this theorem for? So intermediate value theorem can be used to help locate the zeros of a function that is continuous on a closed interval. And the way that we can use it is, let's say we have some polynomial function like this. And let's say that this is x equals to a and b. If the function values at the endpoints are different signs, SIGN, plus minus, there must be at least 1 0 on the interval from A to B. Okay, so if f of A and f of b are different signs, then there must be at least 1 0 on the interval. Right, it would have to cross the x-axis at least once for those function values to be different signs. And you can kind of try and narrow or zoom in to approximate, like make smaller and smaller intervals to approximate where the zeros are. But again, intermediate value theorem is an existence theorem. It doesn't tell us how, it just tells us that they exist. And again, I am just planting the seed. So you've seen this before. We've talked about it a little bit. I'm going to see if I can find some questions that might relate to this class. We would probably have to do with locating zeros. It'll be a bigger deal next year. Any questions so far? Okay, so let's look at an example of finding the zeros of the given polynomial function. Now, the only tools that we have for solving polynomial equations and finding the roots of polynomial equations, right, which is whenever you set the y equal to 0 and solve for x, we only have factoring, and then for quadratics, we can use quadratic formula or completing the square. I group that with quadratic formula. But we don't really have any other methods of locating the zeros of a polynomial. So we're still working with those same tools here. You might notice that what's the greatest common factor of those three terms? So let's factor an x out. And then that quadratic is probably factorable. What is that, x? So if we were to set that equation equal to 0, so set p of x equal to 0, by the zero product property, you would say that x is equal to 0, -4, or +1. These are the solutions or the roots to that equation. And we are solving this equation. Now, these values end up corresponding to the zeros of p of x. They're the same values. But when we think about those values as being the zeros, what we're thinking about, and this is not something you would have to write, I'm just trying to clarify the vocabulary, but it's thinking from this perspective that when you evaluate the polynomial at any of those values, the output is 0. Do you guys understand the difference? So your roots to that equation that's set up end up corresponding to the zeros, which end up corresponding because when they make the function value equal to 0, those correspond to the x-intercepts. Now, if factoring a polynomial, a factor is raised to a power greater than 1, then the corresponding root or 0 is repeated. So for example, this equation, that factors to be x minus 1 squared, right? Which would be x minus 1 times x minus 1, where you could think of the solutions as being one occurring twice. So the solution of 1, or the 1 being a 0, has a multiplicity of 2. Because it occurs twice. So we call this a repeated or a multiple 0 of the function. And the number of times that the 0 repeats is called its multiplicity. Annabelle.
Can we write it like instead of like 1?
Oh, I'm gonna show you how I want you. Yeah, I'm gonna show you how I want you to write it. So our more formal definition of multiplicity of a 0 is if your polynomial has a factor x minus a to the nth power, then a is our 0 with a multiplicity of n. So the exponent to the factor tells us the multiplicity, the number of times it occurs, and a is the 0. And then a note under there, adding the multiplicity yields the degree of the polynomial. So g of x is already in factored form. That could be multiplied out, and you could look at it in general form, but it's in factored form because this is just about identifying the zeros and their multiplicities. Now, it's not really necessary because we're already in factored form. It's not really necessary to go through the step of setting up the equation 0 equals to the right-hand side of that equation and then saying you're solving the equation. It's already in factored form. You can easily identify what the zeros would be, the values that would make the function value 0. So the zeros, just looking at that, the zeros would be 0. What else? What else? What is it? 3/2. Thank you. And 5. Okay. Now, the way that I want you to write this for your zeros and multiplicity is you're going to write the 0, and then in parentheses, we're staying with the way the book does it. You can put mult. I won't make you write out multiplicity. MC. What's the C? What does this? Yeah, I want mult. We're switching to mult. Or multiplicity. I could make you guys write out multiplicity every single time, you guys.
Thank you for letting us write mult.
Okay, so like for 0, that's mult 1. And you're just listing them. -2 is mult. What's this multiplicity? 4. 3/2 would be mult. And then 5 will be mult 1. And the degree of the polynomial, if you add all those multiplicities together, 1 plus 4 plus 5 plus 1, this is an 11th degree polynomial. That's crazy. MC multiplicity. I've seen different ways. I've seen just putting arrows pointing to the 0 and like underneath it listing multiplicities. We're just going to stick with the way the textbook does it. Okay, so let's find a polynomial of degree 6 whose zeros are -3 with a multiplicity of 1, 5 with a multiplicity of 2, and 0 with a multiplicity of 3. If we add that together, 1 plus 2 plus 3, well, that's a 6th degree polynomial. So we don't need to have any extra factors there. I'm going to call the polynomial P of X. Okay, so if I know the 0 is -3 with a multiplicity of 1, how would that translate to the equation of the polynomial?
X plus 3.
X plus 3, which is the same as X minus -3, right? And then 5 with a multiplicity of 2 would be written as and 0 with a multiplicity of 3 can be written as, yeah, just X cubed. You could think of that as being X minus 0 cubed. You can pull the X cubed out front if you want. Multiplication is commutative, so the order of the factors doesn't matter. Easy peasy lemon squeezy. For sketching polynomial functions, we're going to discuss how to determine end behavior. You already know how to find the real zeros, which will correspond to x-intercepts. Then you'll want to determine the multiplicity of the real zeros, and we'll talk about how that helps us graphically with what happens at each of the x-intercepts. And then determining the y-intercept. So basically, intercepts and end behavior are what you're using to sketch the graphs of the polynomials. Your hand up?
When you're listing for zeros with a polynomial, should you list them in like in order?
It doesn't matter. Yeah. Okay, so let's talk end behavior. Anytime we are talking end behavior, we've already talked about end behavior a little bit in here. We're thinking about X approaching positive and negative infinity. Like what is happening to the function values as X gets infinitely small or infinitely large. For polynomial functions, I like to think of whenever we're talking about the function values as X gets infinitely large or infinitely small, I like to think of the terms as being kind of at a tug of war with each other, where the term with the largest exponent, which corresponds to the term where you determine the degree of the polynomial, is going to dominate the other terms every time and win that tug of war. Meaning, when you are determining end behavior, you can just focus on that term that determines the degree. So the term with the largest exponent. Because the polynomial will have the same end behavior as that term, the power function that represents that term. Just to kind of plant another seed, I refer to that, to the y equals a sub n is x times x to the nth power, as the end behavior model of the polynomial function. And the end behavior model is a simpler function that you could easily determine end behavior for, or you know the end behavior of, that has the same end behavior as the more complicated function that you're trying to determine end behavior for. So always thinking, now there's kind of a little cheat shortcut set of rules that you can memorize for determining end behavior of a polynomial function. That's fine if you have those memorized just to be fast with determining the end behavior. But in this class, you should understand that when we are talking end behavior, we're talking about as X gets infinitely large and infinitely small. So as X approaches, right, this arrow, you guys have seen this notation before. I know we've used it once this year. So as X gets infinitely large or infinitely small, what's happening to the y values of the function? Another way to write that is using what we call limit notation. So taking the limit of the function as X approaches positive or negative infinity. We're not going to yet use this notation we're going to use just the arrows for now and think about what y is approaching or what the function is approaching as x approaches positive or negative infinity. So we're going to fill in this chart to go over kind of the rules that you could reference or memorize. So n again is a degree. A sub n represents the lead coefficient. If the degree of the polynomial is even and the leading coefficient is positive, an example of a very simple polynomial that has a even degree and a positive leading coefficient would be like x squared, y equals to x squared, which is a parabola that opens up. Well, any even degreed polynomial function with a positive leading coefficient will have the same end behavior as y equals to x squared, right? Both ends up. Where we can think of that as x approaches negative infinity, y would approach, and if you have for the term where you're determining degree and referencing the leading coefficient, if that's the fourth power or the sixth power, if you think about plugging in very small values like negative 1 million, negative 1 billion, and raising to the fourth power, that value would be very big, very large. And the smaller you input for x, the larger that value would end up being. And then when you multiply it by a positive value, it'll be even larger. So y would end up approaching positive infinity. And then the same thing happens as x approaches positive infinity. Y would end up approaching positive infinity. Even degree negative leading coefficient. My example is very similar, but just with a vertical reflection, right? That would be a parabola that opens down. So even degree polynomial with a negative leading coefficient has the same end behavior, both ends down, as negative x squared. And again, if we think about this, as x approaches negative infinity, when you're raising to that even power, the value is getting very large. And then when you multiply by a negative coefficient, would make the value very small. Annabelle.
So it's the degree of the whole thing, right? Not just like.
Yeah, so the term that has the largest exponent determines the degree of the entire polynomial. Because that term with the largest exponent, as x gets infinitely large or infinitely small, is going to end up dominating all of the other terms. Like the other terms will be, as we approach positive infinity or negative infinity, those other terms are going to be very insignificant. Like if you're cubing a billion and you still have, you maybe have a billion squared plus a billion, like the 1 billion cubed is going to be significantly larger than the sum or the difference of the rest of it. Do you follow that?
No. But so wait, so in like for the one, can you like scroll up to like the example right before this? Like would you use that like the degree of 6 or that the
Yep. So if we were to multiply this out, so since we know this is a 6th-degree polynomial, and just looking at the way the factors are, none of them have a coefficient different than 1. So you know that the term you would be referencing for end behavior would be y equals x to the 6th power.
Oh.
So you would be thinking, okay, as x approaches negative infinity, x to the 6 would be approaching positive infinity.
And if there's more something in front of it, like with that.
It would depend on if it's negative
Oh, okay.
or not. So like if it were, let's say, a -2 in front, that would make approach negative infinity
Yeah.
both directions.
Sorry, I was like trying to misunderstand.
No, that's okay. It's good to ask. Any other questions, you guys? Okay, odd degree polynomial with a positive leading coefficient. My example is a line with a positive slope. You could think of x cubed too, if you prefer. Sid, what are you doing? What you working on? You don't want to listen to the lesson or take notes on the lesson first? I think that would maybe be beneficial. Okay. So odd degree polynomial with a positive leading coefficient will have the same end behavior as a line with a positive slope. So we could say as x approaches negative infinity, y would approach negative infinity, right? So if you have a third degree polynomial, fifth degree polynomial, right? And you're raising a really small negative value to the third power or the fifth power, that's going to give you an even smaller value. So it'll end up approaching negative infinity. And then as x approaches positive infinity, y will also approach positive infinity. And then for the negative leading coefficient, I reference y equals to negative x. So line with a negative slope. So as x approaches negative infinity, y would approach and as x approaches positive infinity, y would approach any question on end behavior yet? We are going to do some examples where we identify end behavior. We'll kind of put it all together to sketch the graphs. Okay, multiplicity of a zero in the graph of a polynomial function. So if the multiplicity is even for a zero, that means that the graph will just touch the x-axis either from above or below. Kind of, I think of it as like bouncing, bouncing off of it. If the degree, or sorry, not the degree, if the multiplicity is odd, it will cross through the x-axis. Now you have to be careful. If the multiplicity is 1, then it will cross, the graph will cross like a line. However, if the multiplicity, the odd multiplicity, is greater than 1, then it will cross in an S shape. Kind of like a cubic. Or the higher the multiplicity, so like 5, would be flatter crossing through, it would be a flatter S shape crossing through the x-axis, or a multiplicity of 7 would be even flatter. But think S shape like x cubed, the chair function. Mhm.
Like, let's say you just like, supposed to like graph it, would you care if it was like how flat it was that you?
As long as I can tell there was an attempt at a S shape, you're fine. As long as it doesn't look like a line, if I were to zoom in, crossing through. Yeah, I'm not gonna distinguish too much between a multiplicity of like 3 and 5. This was a multiplicity of 5, it should be flatter. No, I won't do that. Okay, so let's talk about sketching the graph of this polynomial function. So it's already in factored form. Let's identify the zeros with their multiplicities. So it looks like we have a 0 of 0 with a multiplicity of, and we also have a 0 of, with a multiplicity of 2. Those zeros correspond to our x-intercepts. So we'll have an x-intercept at 0, 0, which will the graph touch or cross? Touch, based on that multiplicity of 2. And then negative 3, 0, touch or cross? Touch. Okay, so we can plot those points. We have 0, 0, negative 3, 0. We know what's going to happen, but we don't know whether from above or below. To determine that, we want to determine the end behavior. What would the degree of this polynomial be? What would it be? 4, right? You just add the multiplicities together. So the even degree polynomial, looking at the leading coefficients of x that's there, when we multiply this out, our leading term would just be x to the 4th, right? Or our end behavior model, which I always abbreviate as EBM, not a technical term. It's more of a Miss Dorset term. Much like MC. So let's think, as x approaches negative infinity, P of x will approach infinity. And as x approaches positive infinity, P of x will approach infinity as well. So that means, okay, do your best. No sharp corners. So thinking end behavior, and then the graph will bounce off of the x-axis. Now, good question. We don't know that. You need calculus to know that. So where the textbook, or did Miss N have you guys do test values in between? You don't have to. You don't have to, because it's an estimate. Even if you did a test value, it would be an estimate. It would be a more accurate picture of the graph, but we are just sketching from what we know. I don't think finding a test value is like deepening your understanding of the graph anymore. And you would still need calculus to determine what that highest point in between was. Okay, so you do not need to do any test points. This is fine. Use end behavior and intercepts to determine what the sketch looks like. Before we move on to the next example, does anyone have any questions? The hump, do you mean? No, that's what I'm saying is you need calculus to determine how high it goes. So you just know that it will go up because we know the behavior at the x-intercepts from the multiplicity, but we don't know how high it will go in between. So for now, you're just sketching So your graphs might look slightly different.
On, the answer keys in the book, would it have the accurate one for the true?
I don't think so. I don't know. They may use, I think they probably use technology for the sketches, so they're probably accurate, but I can't guarantee that.
Who's all the answers in the book? Like, they make them all look the same, so like, the portions of the graphs are all wrong. Like,
They do
portion-
that,
the
huh?
portion is like 10 to 2, and it looks like a straight line.
Yeah.
Oh, yeah.
Oh, yeah, I know you mean it. And then there's somewhere it's like, it goes by 2 on one side and then the other axis, it goes by 1.
Mm-hmm. Yeah, that makes it confusing, or it kind of makes the graphs look different. Okay, you can always check if you want, like, this next one, let's compare our graph with Desmos and see how close we are. Okay, so we still just have, for identifying zeros, factoring and like quadratic formula in our toolbox. GCF of these three terms would be, I'm gonna factor out a negative x squared just to make the next step easier for me, but that's not required, right? I just think it's easier to factor the quadratic with the positive leading coefficient. Oops, that should be x squared. Okay, so then factoring the quadratic factor, that would be +3 minus 1. Okay, so then for our zeros, we'd have 0 with a multiplicity of 2. We would have 1/2 with a multiplicity of 1. And we would have -3 with a multiplicity of 1. So that means our x-intercepts would be 0, 0, touch or cross at 0, 0. Touch. Even multiplicity. 1/2, 0, cross. And it would cross like a line or S shape. Line. -3, 0, touch or cross. Like a line. So we can plot those points. And then let's think end behavior. So we're focusing on -2x to the 4th. So as x approaches -infinity, h of x would approach. Careful. So to the 4th power would be positive values, but then times -2 would be negative values. So it would make it -infinity. And then as x approaches positive infinity, h of x will also approach negative, or will end up approaching negative infinity again. So make sure, do the best that you can to make sure your graph has no sharp corners. Okay, so we cross like a line through -3, 0. Oops, why did it switch to eraser? We'll come up, we don't know how high. It'll touch at 0, 0, come up and then cross. So if we were to compare, where's my Desmos? Here's Desmos. So, yeah, my graph definitely doesn't come up as high, but again, without calculus, we wouldn't be able to determine what that point is. You don't have the tools in your toolbox yet. You could try and pick a test value to get an approximation, a better approximation or better sketch, but it still wouldn't be accurate. We did good. We did good enough. Any questions on that one, or is it okay to move on to the last example? Thank you. Okay, GCF of those terms? Oop, that would be x squared minus 4. What do you mean separate?
Plus 2x minus.
Ooh, what do we call when we do that? What do we call that? We're factoring. We're factoring a difference of 2 squares. I wouldn't call factoring separating, though.
I makes sense, you're like cutting on.
I knew what he meant.
Separating, but they're still
Mhm.
together.
Okay, 0 of 0 has a molt 3. 2 has a molt. Anytime I record, like screen record, it makes my iPad, it makes it January 9th at 9:41 a.m.
That's the
Have you
release
guys-
date of the iPad, because they always release at 9:41, don't they, the Apple thing?
I didn't know that, but that would make sense. That's interesting. Anytime I screen record, it's always January 9th.
When the first iPhone was released.
What year is it though?
2007 is when they released the iPhone. I don't know what date, I think it was.
It's after.
Yeah.
Thank you, Paul. I have been wondering this and voicing this question
I don't know
for
about the
years
date.
now.
I don't know about the January part.
Well, maybe we can confirm that.
Yeah. Jesse, we need to. Oh, I just. We need to cook, we need to cook.
June 29th, yeah. it was-
Oh.
I don't know about the January part, but it was 9:41 is when they released it, and that's like the default time.
But if anywhere this stands for 1, and 1 times 941 is still 1.
If you look at like the promotional, if you look at the promotional photos, like all the iPhones, it's like 9:41.
Interesting.
It's like a black story.
Yeah, it is.
Anyone else?
I thought it was like just a random thing that my iPad did.
I have never seen that before in screencast.
It's only when I screen record. I don't know if it's I don't think it's anytime I share. I think it's only when I record.
That's really-
Okay, so x-intercepts would be 0, 0. What happens at 0, 0? Touch or cross? Crosses like an S. Because the multiplicity is 3. If it were a multiplicity of 1, it would cross like a line. Any odd multiplicity greater than 1, it'll cross like an S shape. So like 3, 5, 7, all will be like an S shape.
Do we have to write the S shape?
No, you don't. So 2, 0, touch or cross?
touch. No, cross.
No touching on this.
Cross is like a line. And then -2, 0 will also cross like a line. So we can plot those points. -2, 0. Okay. And now we want to determine end behavior. So we're focusing on x to the 5th. So we can say as x approaches -infinity, f of x will approach -infinity. And as x approaches +infinity, f of x will approach +infinity, right? It'll have end behavior like a line with a positive slope. So kind of like that. Crosses straight through at -2, 2. And then do your best to make your S shape. Going through 0, 0. What was that?
Oh, yeah. Oh, I need to search.
Yeah.
If you know, you know. If you don't know, you weren't.
So that's pretty good, right? That's what the graph looks like. We did pretty good. I even used the same color.
It's like, cough, cough, cough.
Number 3 is the answer.
Sorry, I have shoulder problems.
If I start seeing arms flailing about during this test,
And said we weren't allowed to stretch on my.
Oh my god, because it was like. Oh, God.
We would cough the number of times, it was like 10 coughs for question 10 and then.
The last question, you have to cough with 25. Name Italian largely is more.
What?
okay, you guys,